Happy Monday. So here we are, we're starting chapter 13 together. Chapter 13 is all about gas laws and the relationships that different properties of gases have with one another and how they impact one another. And the cool thing is we can figure these things out mathematically as well as experientially. So on Friday, you should have accessed a virtual lab where you got to hold some relationships constant and change other properties and see how that affects the gases. And through the worksheet would have discovered that there is three properties that we're going to look at today. We're going to look at the pressure, volume, and temperature of gases and how when you change one or two of these, how it changes the other one as well. Okay, so there were three men that studied gases at different points. Each man focused in on two of these three properties, and we're going to look at their discoveries. And then ultimately what I think is the most useful is we're going to put all of their brains together in a combined equation that is very powerful for us. So let's get started. Let's first start by looking at pressure and volume. A man by the name of Boyle is studied pressure and volume. And as you would have discovered when in the virtual lab, just like he discovered, if you increase the pressure on a gas that's at a constant temperature, you decrease the volume. Likewise, if I increase the volume, I'm going to decrease the pressure. Now, we talked a little bit about this in chapter 12 as well. But what you discovered on Friday is that when one variable increases and the other one decreases, this is called an inverse relationship. Pressure and volume are inversely related. We can calculate how much by multiplying, right? So we show inverse relationships by multiplying. What that means is if I know my initial pressure and my initial volume, and I change one of them, I should be able to calculate the other one. So we write this like this. My initial pressure and volume, my P1 and my V1, is going to be equal to my second pressure and volume multiplied, right? So P1 V1 equals P2 V2. This is known as Boyle's law. Not necessarily important that you remember the name of each of these laws. I'm just putting it out there for history and reference sake. So what that means is, say I start with my gas at 1 atmosphere and 1 liter, but I decide to increase the pressure to 2 atmospheres, I could figure out what the volume was going to decrease to just by doing the algebra, right? 1 times 1 divided by 2 would be 0.5 liters would be what my second volume would be, right? And so this helps us make predictions to plan anytime we're working with gases, okay? Now, another man by the name of Charles, he looked at volume and temperature. And so what he found was as you increased the volume, the temperature increased as well. So as temperature increases, volume also increases, right? When these two things are moving in the same way. So if temperature goes down, volume goes down, right? This is a direct relationship. we show direct relationships mathematically by division. All right, so we're going to use division. So that means that our volume divided by our temperature. So if this is our initial volume and our initial temperature, that's going to be equal to some secondary volume and secondary temperature if we hold the pressure constant, right? So that's what a man by the name of Charles' law. That's what he was doing. He was holding pressure constant, and he was just changing the volume and temperature to see how it affected the other one. And he found this direct relationship. So what this means is if I have, 1 liter of gas at 100 Kelvin. So here's the thing with temperatures and gas laws. This is really, really important. The temperatures must always be in Kelvin. All right, so I'm going to highlight this even for you. We got to really make this important. Must always be in Kelvin. This is because Kelvin never goes negative, right? So if it never goes negative, that also means it can never be 0. And remember from mathematics, you cannot have a 0 in the denominator. It's illogical. So because of that, gas laws always deal with temperature in kelvins. Remember to convert from Celsius to Kelvin, you add 273 degrees, or 273, and you get the Kelvin. All right, so if we've got 1 liter at 100 Kelvin, and we change the volume to maybe 0.5 liters, what would be the new temperature, right? So remember again from algebra, when you've got a ratio set up like this, you can cross multiply to find out what this equals. So what this equals is 100 Kelvin times 0.5 liters equals 1 liter times the secondary temperature, or just 50 Kelvin. I tried to do that in my head. Hopefully I did it right. Let me double check. The way my day's going, anything's possible. 100 times 0.5. Yeah, 50. Great. This is Charles's law. Okay. Our last of the 3 men was a man named Guy Lussac. And what he did was he looked at pressure and temperature. Right? And he found that, again, as temperature went up, the pressure went up. Or as pressure went up, the temperature went up. Likewise, if one went down, the other one went down. So just like we talked about with Charles's law, this type of relationship is a direct relationship. It's going to be shown mathematically by division. So Guy-Lussac's law says P1 over T1 equals P2 over T2, right? So whatever my initial pressure and temperature situation is, if I keep that volume constant, I should be able to predict if I change one of them, what it does to the other one. So let's look at this. If I start with 1 atmosphere of pressure at 100 Kelvin, and I increase that temperature to 200 Kelvin, could I predict what my pressure was going to be? Well, sure. Again, cross multiply, and you get 100 Kelvin times my pressure equals 200 Kelvin times 1 atmosphere. If I divide by 100, my new pressure is going to be 2 atmospheres. right? And that's just what these laws are beneficial. Now, each of these three laws, Boyle's law, Charles' law, and Gay-Lussac's law, assumes that you're keeping the third property constant. So let's look up here. In Boyle's law, we were looking at pressure and volume. That means we kept temperature constant. Constant means it did not change. In Charles's law, we were looking at volume and temperature. We assumed we kept pressure constant. And then finally, in Gay-Lussac's law, we looked at pressure and temperature, which means we kept volume constant. Now, that's not always the case. In real life, you don't always get the opportunity to keep something constant. So when we look at all three of these men's discoveries, we see that there's a bigger relationship going on here. And what we're able to do is we're able to combine into what is called the combined gas law. And really, in my opinion, this is the only gas law you need to learn, because I'm going to show you how to use the combined gas law for every single gas law problem where you're looking at initial properties and changing something to calculate new properties, right? You don't have to learn distinct Charles, Boyle's, which one do I use? Just always go to the combined gas law. So let's look at these and see how we can combine them. Well, remember, Boyle's law just said that P1V1 equaled P2V2. Charles's law said that V1 over T1 equaled V2 over T2. And then Gay-Lussac's law said that P1 over T1 equaled P2 over T2. Well, if I was more fancy with technology, I'd kind of take all of these and just kind of whoosh them all together. And when you do that, you get something that looks like this. P1V1 over T1 is equal to P2V2 over T2. This is the combined gas law. This is very powerful, and it is what I'm going to encourage you to use on every single one of your homework assignments today. In the next video, I'm going to show you how to work through some demo problems using only this combined gas law and how it works when you're holding something constant or whether you're holding nothing constant. All right, so go ahead, take a moment, stretch, get something to drink, and then meet me again for the second video. Bye-bye.